So on our topic of limits, I just thought we would go over a visual example, and then actually before that, I just wanted to go over the notation because that can be a little difficult to read for the first time if you already haven't watched one of the other videos from usually Khan Academy. But I just wanted to show, for example, what the notation means. So if we want to find the limit, so LAM, but the limit, let's say we're talking about here, the first one on the left, so at x equals -6. Obviously, x equals -6 anywhere on this line, but as indicated by our dashed line, it tells us we have a vertical asymptote. Just means that our graph is going to approach it on either side, but it'll never actually cross. And you can never cross a vertical asymptote because it's telling you that the x value causes a function to be undefined. But obviously we have a left side of that vertical asymptote and a right side of the vertical asymptote. And so when we talk about limits, are we referring to the left-hand side or the right side or the two-handed limit? So the three notations here. So when we say the limit as x approaches -6, so we're talking about the x value, so that's along the x-axis, specifically at -6, and the little negative sign up here in the superscript position just tells us from what side of -6. So in this case, we're talking about from the left side of -6 or the negative side of -6. And f of x is just the generic function name. And a lot of times, like I said in the notes, we don't necessarily have a formula for the function, so we just give it a generic name. And then the x here just tells us that's the input value. Again, another generic, kind of like a dummy variable. But whenever we see something like the limit as x approaches -6 from the left, our function is going to approach, and in this case, it's positive infinity. And I like to write that just so that I know that I meant positive and not just there is no misunderstanding of, well, was it negative? But you could just leave off the plus sign if you wanted to. Anyways, so on our graph, what this looks like is, again, here's -6. Well, one place where it's x is -6. But as we talk about approaching -6 from the left side, we're just coming from this direction. So if we come at the -6 in the x direction, it would be along the x-axis there. But we're concerned about what the function is doing. And the function to the left of -6, as we keep going left, is going to keep going down. But as we get closer to -6, we're going to get how we do that is not along the x-axis, but along this blue line. So if we were to track, we would track up, and the arrow tells us that we're going to keep going. And then also the vertical asymptote tells us that we can't go anywhere this way, but it just tells us that we're going up. So as I approach -6 from the left, I'm actually going to do so vertically. So, so as x goes this way, f of x is going to go that way. And so we get positive infinity. And technically, positive infinity is not a number. L has to be a real number. And since positive infinity is not actually a real number, technically that left-hand limit does not exist. But for notation purposes, this actually tells us a whole lot more. If we just said does not exist, well, does it just stop? You know, what's going on there? And so the positive infinity tells us better where the graph is going, but technically there is no limit to where it is going. It is just going off to infinity in the positive direction. So then the other superscript, denoted with the plus sign, tells us again the limit as x approaches -6 from the right or the positive side of the graph. In this case, this tells us it's going to negative infinity. So even without looking at the graph, I can say if I'm approaching -6 from this side, my function is going to be going down forever. And we can verify that with the graph. So again, here's -6 on the x-axis. As we approach -6 this way, all of our x's are getting closer and closer to -6. And we have to be really careful when we talk about closer and closer. Obviously, we start way over here. There's a whole bunch of stuff going on. So we were talking relatively close to -6, and there's a little discussion in the textbook. I think there's an asterisk at the bottom of the page that talks about what we mean by relatively close, or I forget the words they use there. But if here's what we're trying to approach, we're going to stay in this little segment. And again, as x approaches -6 from the right side, the function is actually going down to negative infinity. Since your left and right hand limits miss each other, they go off in either direction, it just tells us that our function does not exist. And the next one here I think is a little bit easier. We'll use an analogy. So say here at -4 is a meeting time. You want to meet someone at, if -4 were the time. I know, it doesn't make sense, but just roll with me here. But one of you is coming from one direction, the other is coming from the other direction. So if you were coming from the left of -4, you're following this trail. And each of these values along the y function values are tied to some point in time on the x. So as you're coming to the location at -4, you reach a height of 2. So maybe that's the drop a pin and you're at 2. Very easy GPS location here. So from the left of -4, you would reach a location of 2. This one is a closed circle, meaning you would actually land at 2 and you would physically say, hey, I'm here at 2. Well, then your buddy is coming from the right of -4. So they're going along this track up here. And when they get close to where they should be at -4, what happens is, well, one, this is an open circle. I know it doesn't quite look like it on the page there, but this is supposed to be an open circle. But I kind of like how the marker bled. If I could actually be part of that space, losing words here, if you could actually occupy, there's the word, occupy that space, you would technically be at -4, you would technically be at a height of 3. And so in that case, your left-hand limit would actually be at 2, but your right-hand limit would actually be at 3. So 2 separate values, 2 separate questions, but if we wanted to find, and here's the notation for the two-handed limit, so there is no denoted plus or minus, that is meaning from left and right at the same time. So not 2 separate individuals, but if you could come together, where would you be? And in this case, you can't be at infinity, but also because your left and right hand limits do not match. That's why we get the does not exist. So back at our graph here, we also have a two-sided limit. Two-handed limit means the same thing, does not exist because your left-hand limit puts you at one location and the right-hand limit puts you at a separate location. And obviously you can't have a meeting if you're at 2 different locations. No Wi-Fi and FaceTime and all that kind of fun stuff does not exist in this example. But let's say back in the old school, if you were here and your friend was here, there would be no meeting. And so in that case, your limit does not exist. Now, the next one is kind of an interesting one. And notice how we're skipping over these continuous pieces, kind of skipping ahead to the next section. We talk about continuity. The reason why we like continuity is because we have a really defined value. So if I wanted to say what's the limit as x approaches -2, you would just say, well, hey, what's f of -2? I don't know the function values for these specific places, so I could guess it's about 3.5, but we wouldn't have to guess, well, what's the left side, what was the right side, because of that continuity, the limit value is the function value at -2. So going back to 0, the reason why we stop here is because we have another, we call it in this case is a missing value. So we're discontinuous at x equals 0. So again, now if I approach 0 from the left side, I'm at, and I think your book says that this is a 3.4, about 3.5. It's halfway between 3 and 4. But for the sake of the example, we'll stick with the 3.4. So the limit from the left is 3.4. The limit from the right is 3.4. So technically the limit exists and is 3.4. Even though the function does not exist there. This would be an example of if you approach from the left and your buddy approaches from the right, and this is like a massive sinkhole where the restaurant was supposed to be. You can see each other, you would totally have the meeting if the restaurant was there, but since it's not, It just means that the function doesn't exist, but it doesn't necessarily mean that the limit doesn't exist. So the limit in this case would be 3.4. Again, I know some of the analogies lose water in some of these, but the idea is that the left-hand limit matches the right-hand limit. The limit exists and is that value. Oh, and I was just reading, it's really light here in gray. It says, even though f of 0 equals 2, sorry about that, I forgot to color in. There is a solid dot here at 2. We call that a removable discontinuity. And all that means is that, well, I've just removed that location, and it looks like, well, instead they just moved the restaurant without telling someone. So if you can kind of envision, there's a massive sinkhole, and all they did was they just moved it down the street or whatever. Similar to our other asymptote example earlier at x equals 3, you might be thinking here the left-hand limit. So as x approaches 3 from the left side, our graph goes down. As x approaches 3 from the right side, the graph goes down. Both sides go to negative infinity. So you're like, hey, over here, the left hand and right hand were the same. The limit existed and it was that value. But you have to remember that the notation there is it equals an actual limit value, L being a real number. And in this case, infinity, negative infinity is not a real number. And then the other two are going to be the same. It is also discontinuous at 4. In this case, it doesn't look like they have filled in the gap anywhere. So this would just be an actual hole in the graph. There's nowhere else that the function exists at x equals 4, but the limit would exist, and it looks like it would be at 1. So again, if the graph did exist at that one little spot, the value would be 1. So as you approach from the left of 4, so the left of 4 would be here. So again, relatively close by, but from the left of 4, the graph increases to 1. And then from the right of 4, the graph decreases to 1. And so your limit would be 1. So again, anywhere your graph is continuous, we really don't have to ask the left and right hand limit questions. We could just go from the two-sided limit at the same time. So I think the one that they have here is at x equals 6. Because there's no denotion of an open circle or an asymptote, is really the only two where you can have a discontinuity. There's no break in the graph. So in this case, they are telling us that at 6, the function value is 2. So being continuous is pretty important. I did want to mention a couple of these rules, and I've got the asterisk there by number 4. Again, when we talk about, it says the limit as x approaches a of f of x, we don't need to know what the function is. If we do, that's awesome, but this is telling us a is a known value. So the ones in the homework will give you like the number 5, and then the limit of g of x as x approaches a is b, so it might be 2. So all of these are kind of just getting you comfortable with notation, but again, if k is a constant, and you'll see that pretty consistently, k being a known constant or a value we could know. The limit of a constant function you could think about as a straight line. Constant functions remain constant, so the limit again would be continuous. The limit would just equal that constant value. So what makes that what helps in the next piece there is if I do have a constant times a function. So let's say the limit of 2x as x approaches some number, it's really just going to be twice the limit of that variable portion, basically. And so it would just be k times whatever the limit of that function is, so a. And then sums and differences are always great. We can split them apart. So the limit of, and then so the brackets say that I've got a function plus another function. It's just an individual function, so that's what this means. So the individual limit of function f plus or minus the individual limit of function g, and it just means that we're going to add those two values together. So it just underneath it, it kind of explains the limit of a sum or difference is the sum or difference of the limits. And I know that doesn't make a whole lot of sense right now, but when we get into integration at the very end of this semester, I know it seems like a while away, but 8 weeks is going to go pretty quick. But we'll see how that's really nice if we can separate things into two or more pieces. A lot of times their individual parts are a lot easier to deal with, especially when we're talking about multiplication. So the one that I did want to get to is number 4 here. So similarly, the limit of a product is the product of the limits. The limit of the quotient is the quotient of the limits, but provided that the denominator has a limit that exists for that value. So in this case, we can't let the limit as x approaches a of g of x be 0. And in the notes, we talk about what happens if the numerator and denominator both have limits that equal 0. And a lot of this is going to come back to algebra, really being familiar with those, especially rational functions, because that's what this is, just a fraction. Rational just means fraction. And so knowing the properties of those rational functions. And that's really all we're doing. If I had a function, basically, in equation form, and let's say I did not have this graph, if I only had the equation, how could I then determine those limits? And that's where the homework and the rest of the notes go, and I'll leave that for now. But if you have any other questions that come up, please do not hesitate to email me.